Hey everyone, welcome to the walkthrough for homework 4, question 4. This question is about the hematocrit as well as blood flow. So let's get started by just reading the question. So we have blood flow through a tube and we have radius of the tube, 25 micrometers, and then we have a length of 1000 micrometers. And then additionally, after that, we're also given the pressure drop across the tube is 30 mmHg. Then we have the hematocrit. We're given something called the discharge hematocrit, which we'll talk about in a moment. It is 45% denoted by HD. We have the plasma viscosity at 1.03 CP. And then we also have a way that we can model this tube, where we have two immiscible layers. We have a plasma layer with a thickness of 4 micrometers and a blood core region, and the radius is 21 micrometers. So always the first step would be to draw out a model of this. So we're going to model this with a tube right over here. Great. And then we essentially have a smaller tube inside. Sorry for my drawing skills. Great. And essentially, this is our core, and the blue is our core blood region. And we know from the prompt, it says 21 micrometers is the radius. And then we know that right here, this thickness is 4 micrometers. And then we have blood flow this way, out that way. And we also know a couple things. We know radius of the tube is 25 micrometers. We also know the length is 1000 micrometers. And we also know the pressure drop is 30 mmHg. Great. So now that we have that down, we also know that the discharge hematocrit is 45%. And let's just take a look at the question really quickly. It's asking us to compute the hematocrit of the blood in the core region. And then we're also asked to find the tube hematocrit. So let's just quickly talk about the differences between those two. First, the discharge hematocrit is defined as HD. This is the discharge hematocrit. And essentially, this is the volume fraction of red blood cells inside the vessel, which is delivered by flow. So we have right over here, it's the volume fraction. Red blood cells in blood delivered by flow. And essentially, this is velocity dependent, right? So if we have a faster velocity, we can expect a higher discharge hematocrit. And if we have a slower velocity, we can expect a lower or even sometimes almost zero discharge hematocrit. You can think of it as how much of the flow is discharging the amount of red blood cells, like that volume fraction, right? So just keep that in mind. We also know from this that we know the discharge hematocrit for this question is 45%. Then now we have something called the tube hematocrit. And the name gives it away. It's essentially all the volume fraction of red blood cells inside the specific tube that we are looking at. So let me just write that down. So we have the volume fraction of red blood cells. And this is inside the vessel. So exactly as it means, it just defines the volume percent of the red blood cells inside the capillary tube that we are examining. So we do not know this. We know the discharge hematocrit, and it's also asking us to find some, I'm going to denote it by 0, right? But essentially this is the hematocrit of the blood in the core region, right? Of core blood region. So it's essential that we're identifying that we have three different hematocrits. We have one, and then now the goal is to find HT and H0, right? So great, let's keep going. So we're going to use a handy equation from the textbook. I believe it's not in the pre-reading lecture notes, but if you go into the textbook section where those notes are pulled from, you'll see this equation. So I'm going to actually repaste it over here just so we can all take a look. This essentially relates the tube hematocrit to the discharge hematocrit. And it's a really great relation because we will need this. Essentially what we're going to do is we're going to move this over here to the numerator, and then we can solve for HT. So we, over here, I do want to define some further terms. RC is the radius of the red blood cell, or whatever is in question, right? In this case, it's the red blood cell. From the pre-reading, you'll also see that the diameter of a red blood cell is 7.65 micrometers. So that means that the radius of a red blood cell is 3.825 micrometers. And this is what we're going to be using for that RC value. Great. So we're going to keep going. Now that we have RC, sorry, I don't want to hide that square. R, we defined it. It's the radius of the vessel. And we know from this, it's not 21, it's going to be 25. We're looking at the entire vessel, right? Although it says there's a wall of thickness of 4 micrometers for that plasma layer, it is still in the tube that we're looking at. So we're going to be using a radius of 25 micrometers. Great, so now we can solve for tube hematocrit. And then I'm just rewriting this over here. Great, and keep in mind, so we know the discharge hematocrit. We're given this in the beginning of the question. So we'll essentially plug that in, and then you should have something as your answer. HT equals something. Great. Now let's keep going. Let's talk about, and this will be in a percent as well. Now let's talk about, what about our hematocrit of the core blood region? So essentially, let's think about this, right? We know the tube hematocrit, and we can essentially use that and make an assumption that if we have our tube, I'm just going to draw it out very roughly right over here. If we have a tube right over here, we know that flow velocity is 0, right? At the wall. Essentially, there's no flow, right? We can essentially assume that the local hematocrit value at the wall is 0 in the region near the wall. So, and over here, we can assume that this is our unknown H0. We're essentially relating HT in this kind of distribution pattern. We have H0 over here, and we have V0 over here, and this is a hematocrit of 0, right? So with that being said, I'm going to erase this just so we can have some more space. We're going to use this relation from the pre-lecture reading. Great. So as you can see right over here, when we have the hematocrit is this H0, right? This core region, right, of the blood that we defined earlier right over here, right? We're going to say the radius is all the way from the radius to RC, right, which is the red blood cell radius. And then we're going to say that for this, right, we have essentially 0 for RC, right? Hope that makes sense. Great. So essentially now let's rearrange this to solve for H0, right? Essentially what we would do is we're going to bring this term over here and we will have an expression that looks like this. And I'm going to write it out right over here. So we have H0 equals HT over 1 minus radius of the red blood cell over R. And essentially, we will use the HT value, right, that we find right over here. So essentially, it's a several step process, and we'll use it to find H0. And then you should have something that solves for H0 in terms of percent. And that will be, this is an assumption we make to find the actual core region of that core blood region and the specific hematocrit there. Great, so let's move on to part 2, part B. Actually, let me write this out, part A. And then B, it's asking us to estimate the viscosity of blood in the core region. Great, so let's keep going. We have to find the viscosity. Well, the great thing is also in the pre-lecture notes, there is a relationship to find the actual viscosity. And actually it's specific for the 45% at HD equals 45. So this specific equation that I'm going to put on the screen right now is related directly to when HD is 45%. And we have this right here, right? So you can see even that 45% is within here. So that is a factor. So remember, we can use eta, we can use mu, same thing as we talked about in class. Great. So essentially, in this case, the diameter, right, is this diameter of vessel, right? And we know the radius is 25 micrometers. That means diameter is 50, right? So essentially, all you're doing in this is plugging in for the terms, just one term actually, just the term diameter, right? So let's write this out. And then we can just write, you can just plug in 50 micrometers as is, by the way. So we have 220 times e raised to the negative 1.3 times 50 micrometers plus 3.2, and that's on its own, minus 2.44 times e to the negative 0.06, and again 50 micrometers raised to the 0.645 power. Okay, so it's really important that we're very careful with our math on this. I suggest do this term first, then this, and then kind of combine them all together to get your final answer for that viscosity. So you should have an answer in units of CP. Great. So that's just for part B, so that's great. And let's move into, actually, I apologize, that is not the end. So we found essentially this, let's actually write right here, not final answer. So remember, we just calculated the average viscosity of the entire tube, right? The entire tube, rather than just the blood core region, which is what the question is asking for. So the question is, how do we actually find the specific core blood region viscosity? Well, we're just going to use some simple geometry. I'm going to draw a cross-sectional area. Cross-sectional area, right, of what we're looking at. And we have right over here, we have a radius R, big radius R. Then we have right here, we can, oh no, okay. We can say this is just small r, B for blood, B for blood, right? So radius of the blood. And we know that this is 21 micrometers, right? And we know big R is 25 micrometers. Great. So essentially what we're going to do is we're going to just relate the viscosities per their cross-sectional area. So we have the viscosity that we obtained earlier, right, for the entire tube denoted by R. And essentially we're going to multiply that by the cross-sectional area of the actual entire tube, right? And we know this will be equal to the viscosity of the, actually, let's do the blood first. Of the blood, right, the internal area, we're going to essentially examine this section first, right? And then after that, we're going to do this section and add those two together to get that total viscosity times cross-sectional area, right? Essentially, that is what we're doing. So just give me a second, just pressing back. Okay. So of the blood region, we know that's times pi RB squared, right? The small radius. And look at that. This is what we're actually looking for. We're looking for that viscosity of the core blood region. So when we're doing this, we need to make sure that we know that the terms that we're looking for are in the expressions that we are writing. So that's just really important to keep in mind. If you're not seeing a term for the blood viscosity, then something's not set up correctly. So just keep that in mind as we're doing these kinds of questions. Now, let's keep going. Plus, we know then the plasma viscosity, right, times the cross, this area, right, that we just drew right over here. I'm not going to redraw that. But let's keep this in mind. So this was a big issue on the midterm that a lot of people struggled with. But when we're talking about cross-sectional area between two circles, right, that we're drawing, we cannot just simply, let's see, we have R minus RB, right? It is not correct to just square this, right? These are absolutely not equal, right? This one actually is taking the cross-sectional area or the area, right, of two circles and subtracting those areas, giving us only this, right? Only this. But essentially what this is doing is it's only, in our case, it's 25 minus 4, right? So, or 21 is 4. So that just makes a small circle of radius 4. That's not right. That's not the actual area we're looking for. So we need to always remember that we are using this, right? The squares cannot just, you cannot just do that. You absolutely cannot do that, right? So just keep that in mind. I'm going to erase this right over here. So what does that mean? That means that the radius is going to be R squared minus RB squared, right? We're going to keep those squares inside our expression. Great. So essentially now all we want to do, also one quick note, we know this. We know this, and I believe it's 1.03. Yep, 1.03 CP. Great. Would you look at that? And I guess the essential thing also is just knowing what we do know. Yeah, we know this, we know this, we know this, we know this, we know this and this. And all we're doing now is we're solving for RB. Or sorry, not RB. We're solving for the viscosity of B, of blood, right? So essentially, your answer should be rearranged, right? Rearranged to RB. Or I keep saying RB, I apologize. It's A to B, which is just the viscosity of blood, right? We rearrange for that term, and then with unit CP. And this is your final answer. Great. Great, so that's just part B. Now let's go to part C. And let's take a look at the question one more time. It says specify the boundary conditions, right? Specify the boundary conditions necessary to find the 4 unknown coefficients that arise in the plasma and core velocity equations. Okay, so it's asking for what are the BCs, boundary conditions, right? 4 unknown coefficients, coefs, right? And then especially we have like the 2 layers, right? Blood and plasma. So we know, like, for example, when we're looking at a boundary question or boundary condition question, we could have, for example, 2 fluids, immiscible fluids, and we know several conditions, right? First, we know that the velocity is 0. We know here, velocity of 1 is equal to velocity of 2, and we also know that tau of fluid 1 and fluid 2 are equal. And then we have some other boundary conditions as well, but yeah, tau being shear stress, and velocity. And we have some other boundary conditions as well. We have like the maximum velocity in the middle, for example, but essentially let's just write it out. The first, second, we know the first boundary condition, right? We know the velocity at, now we can also kind of look at this above image as an example, but we know that the velocity when the radius is at R, right? Outside, all around the outside here. Maybe I'll use a different color. All around the outside here, the velocity is 0, right? So we know that the velocity in the Z direction, right? Z direction, this is Z. We have R, we have theta, right? It's in the Z direction. We want to specify what direction we're talking about. And the R radius, or small r, right? It's varying. Radius equals big R is 0, right? So we know that boundary condition, that's for sure. Now, what are the 4 unknown coefficients? Well, I guess we don't really know the velocity between blood and plasma, right? We also do not know the shear stress, right? I'm gonna just blood and plasma like that. We also don't know the max velocity, right? In core blood. And we also don't know the max shear stress, right? Or the shear stress at this point, at this maximum velocity as well. We don't know those things. So it's really important that we kind of make sure we have all of these terms in our boundary conditions, because that's what the question is asking for. Well, I hope you all know this and this boundary condition, right? That can be easily written as I'm not going to write it in this notation, but you all can do it. The blood at radius is RC in Z direction, right? velocity and then plasma at R equals RC is equal to the velocity and then equal to shear stress. And then please write it out in this form right here. Right in this form. Sorry, the arrow should be going the other direction. Okay. Right in this form, right? And then for our third last one to relate these two, right? Essentially, we know that these terms, we can't really determine the terms themselves or the values, but we can write that they are a finite number, that they're not infinite, they're not zero. So you can essentially write something like the velocity for in the z direction at r equals 0, right? For the blood, right? There's a hint for how to write for the second boundary condition. And you can also write for shear stress. Please write it out. And then you can just say they are finite, right? They're not infinite and non-zero. Actually, it could be non-zero. So let's keep this out. Let's just say it's finite. So great. So we essentially now we're checking off what the question is asking for. Yep, we have our boundary conditions. We have our 4 unknown coefficients because of the blood and plasma interface, right? Because they're immiscible. All right, so that is the end for homework question 4. I know that homework 4 is extended to tomorrow. So if you do have any questions, please send me an email. I'm more than happy to help. But I hope you all have a great rest of your day.